Okay, I think we're ready to start up again. We've got a...
We're going to go into new territory, Steve.
So we've got a lot of talks this afternoon, and then a chance for more discussion. Before I get started, this morning we neglected to acknowledge Mei Ling Rodham, who's our Sea Grant State Fellow, and she's sitting back there hiding, but she's done a great job helping with this workshop, so I want to acknowledge her. Thanks. John.
Yeah. We good? Are we live, folks? Yeah. And I'll keep away from here. I'm told I tend to swallow the mic, so I'll try and stay away from it a little bit. So the title that Sam put out was Hydrodynamics, and I figured, given Bruce was going to do the background on the Delta, that he would cover a lot of the basic hydrodynamics, and I wasn't wrong. And so what I wanted to do is talk about looking at the interaction between salmon outmigrants and hydrodynamics. And this comes to your point, Kenny, about trying to match management timescales with fisheries timescales. And with this study, we're really fortunate that, or studies that we've been doing, is that we're collecting salmon data at the same time scale we're collecting hydrodynamic data, and we have a lot of data. And so the idea here is, instead of using the management timescales to figure out what the fish are doing, we're trying to get at the mechanics of what fish are doing at the same timescales, and then trying to ramp that up to see if we can collapse it to the management timescales. So this is going to be a little bit more process-oriented, a little less, graphs of abundance or whatever. So it's going to be a little bit different. And I'm going to set up my colleague, Russ Perry, who's going to look at survival throughout the whole delta. So that's kind of the plan. So I do need to acknowledge we've done a number of acoustic telemetry studies in the North Delta. Pat talked about the South Delta. We started a big study. I think Steve and maybe you were on the panel, Kenny. Yeah. Anyway, we actually did that. We were going to release 6,000 fish, and then we got caught up in the bond crisis and had to actually stop mid-study with a lot of equipment out and fish out and so forth. And then the Bureau stepped up, and we're now sort of finishing up our 2008 analysis simply because we had a number of years that we couldn't get at the data because we didn't have the funding. And then more recently I've been working with DWR at looking at an acoustic, a series of barriers at Georgiana Slough. And so if you're unfamiliar with the Delta, the Georgiana Slough is this like really wimpy looking thing, but we're spending a gob of money trying to keep salmon from going into the Central Delta through Georgiana Slough. So it doesn't sound like much of a place, but it's actually pretty important. So there we go. So, why should the State Board care about route selection in the Delta? And I'm going to. The reason they should care is that, and Russ will get into this a little more, is that there's a couple key junctions in the Northern Delta that really determine the fish's fate. If you go down Sutter or Steamboat, you have a very different outcome than if you go down Georgiana or the Delta Cross Channel. And so we want to try and understand why fish in these experiments, or at least a part of these experiments, why fish go where they go. Initially, we had hoped that fish would go with the flow or the net flow or the tidal flow, but it's actually, as you might expect, a lot more complicated than that. And so that's what I want to talk about today. But the State Board should be interested in this because they do have influence over the net of the inflows and outflows and hydrographs and so forth. And as you'll see in my talk, that has a great deal of influence on how fish react to junctions, right? So first, basic hydrodynamics, and this is my version of Bruce's slide. And one of the reasons I'm going to actually do it, you want to wiggle that and get it going? There we go. So again, the arrows are scaled to the tidal flow going back and forth, and you can see the blue arrows are the net flow. And to a large extent, the State Board and others talk about the Delta with regard to the dark blue arrows and not the light blue arrows. And Bruce and Matt talked about the Delta being a lake. I really don't like that. I think the fish assemblages, I'm certain that they know a lot about, and they're probably freshwater fish assemblages, but this is a freshwater tidal lagoon. This is not a lake, and lake implies, limnology and turnovers and all kinds of stuff. This particular system doesn't even stratify in most places. Lakes do, and the energetics, particularly because this is a bunch of canals, are quite strong. So this is a freshwater tidal lagoon. Let's stick with that. So there's a lot of tidal influence. And what's important, the other important thing to recognize is that fish or particles, this is a model result from RMA, go long distances every single tide. These are actually shorter than what can happen on the surface. On the surface, if your cooler goes overboard, you're looking at 8 miles, tidal excursion, okay? So as you might imagine, this makes it very challenging to sample for fisheries or anything in the water because, you know, at the end of an ebb tide, the fish can be like at Chips Island, and then 6 hours later, they're 8 miles away if they just go with the flow. So it makes things really challenging. The other thing to notice is there's all this dispersion kind of down by the bay here, and then in this really channelized place, there's almost none. So there's a lot of variability in some of the things that Steve was questioning people about. Residence time, because the tides here are very, very low. Residence time here, even though it's sloshing back and forth, is actually pretty large. All right, so that's that. So that's particles and that's hydrodynamics, but what do the fish do? Wiggle on that little guy? So this is some radio tag results that Dave Vogel got years ago. He's actually following these guys around a boat, and if you notice, they go sloshing around with the tides too. So that's a Sacramento fish release at Ride. You want to do that again real quick? This is one of the important things about geometry. You'll see it's pretty riverine in the Sacramento River. The fish are generally going downstream. When they go into that widened area there, boom, within meters, they're in a completely different place. The tidal excursions and the influence of the tide as you go from the Sacramento River to Cache Slough is extraordinary. Now, go to the next slide. Or I can do it. There you go. Let me go to the next slide. Now, go ahead and wiggle it and start it. Here's a release, again, by Dave Vogel on Georgiana. Pretty unidirectional until you have that big change in geometry down here at the San Joaquin, and then they start going back and forth. So I'm going to show you this. Pretty tidal up in here, but when you get into these big areas in the western and central delta, the tides are, you know, and I think Brad's probably going to talk about this, are extremely important. And these, again, are not particles. These are not models. These are actually tagged fish. All right. So I want to talk about junctions. And so why do you care about the tides and junctions? And so this is some recent data. Actually, can you stop that? Let me back up and then go here. I can't get the map back. Anyway, this junction is Steamboat Slough. It's very close to us. And I have a map over there that shows that it's almost in the city of Sacramento. And you'd think, oh, that's dominated by the river. And so this is some recent data we collected. We have a couple of velocity profilers out here, actually right now. I think, what's the date on this? Yeah, it's like pretty soon. So what I'm going to do is have him wiggle this thing, and we're going to look at the flows here. It's Steamboat Slough, very close to where we are. It's, you know, this is what you'd expect, right? The river's going downstream here. And then, what happened? The flows reverse, and you can see a really nice pattern here. The flows actually reverse and go upstream. Interestingly, Sutter Slough is going the other way. So there's a convergence right here. And one of the things that we noticed is that Sutter Slough upstream, and I don't have my map, entrains a lot of fish. And the reason is it has this period of time where everything's going into Sutter Slough. So I'm going to make this point now, and I'm going to make it later. The net flows influence salmon survival by their influence on the tides. And at junctions, by their influence of how they affect the velocity distributions in these channels. Because as you saw, that's a really complicated flow pattern that occurs. And when the state board does its mandates on how the hydrologic cycle influence, that will influence entrainment in all of these junctions. So most of our studies have not been in Southern Steamboat Slough, which, by the way, is right here. So these two channels right here is what I was just talking about. Freeport is our gauge, USGS gauge, that measures the discharge in the Sacramento River. And, of course, this fall, under really low flow conditions, it was going backwards significantly and for a long period of time, longer than we've ever measured. So this summer, I expect we're going to get very significant flow reversals, even as far as Freeport and maybe even up at the city of Sacramento. So anyway, here's the junctions that we've been studying for a long time. And as I pointed out, Georgiana Slough is a big deal because it goes down, and Bruce talked about this and others talked about this. This doesn't have a gate on it. It goes down to the central delta, where Rush will show us that salmon survival is pretty low. This Delta Cross Channel has a gate on it, which is closed right now. The nymphs closes it to keep salmon from going down to the central delta as well. So this is the junction that we're studying, and you want to wiggle on that and see if you can get it going. So these are streamlines. They don't show the strength of the velocity. The gate's closed right here, but in a minute it's going to open. And then we're going to see the effect of the tides on this system. And so this is what fish are experiencing over a 24-hour day at this location. You're supposed to go, holy hell, how are you going to figure out what fish are doing in that system? And that's what this talk is going to be about, trying to figure out what fish are doing in this kind of very, very dynamic environment. Right? So the tides, again, are extremely important for these kind of things. So the first question I'm going to sort of address with the very detailed data we've been collecting at Georgiana Slough and Delta Cross Channel is, do fish go with the flow? This would be a very nice result. All you need to do is figure out the ratio of the flow split, then you'd be able to figure out where fish are going. Because we can measure the flow really easily. So, and that depends on what you mean by flow. And so what we're finding I'm going to give a conclusion here at Delta Cross Channel and Georgiana Slough is that juvenile salmon don't go with the tidal and net discharge in general. And that juvenile salmon do go with the tidal time scale surface velocity distributions. And hopefully I'll get all the way to the end of my talk and I'll be able to show you that that's actually the case. If we can really get the surface water distributions understood and we know the fish distributions, we can predict where they go very accurately. So our challenge, and this is what I was talking about when I first started my presentation, is our challenge is to take these very, very detailed measurements that are really expensive to get and scale them up to something that the managers can use like OMR or something else. So that's the kind of the approach. So thankfully people have talked about acoustic telemetry studies. I want to make a couple of points about this. We're releasing 5,000 fish. We're doing it differently than they do at the VAMP, which is where they try and hold everything constant and then they release fish for a couple days and then they go through the system. What we're doing here is we're releasing 5,000 fish, but we're releasing 100 and so a day, every couple hours for 24 hours. So we're releasing way up in the city of Sacramento, so they have a couple day-night cycles to acclimate. And so this continuous release has a lot of advantages, and to be able to do that, you need a lot of fish. Also, to be able to understand spatial distributions and how fish are interacting with the hydrodynamics, you need a lot of fish. You need a big sample size, right, to be able to figure that out. So a little bit different than some of the stuff Pat's done. So 2 talks here. I'm going to talk about what goes on in these junctions here, and we do that as far as the fish goes by putting out a bunch of hydrophones, and then we can track fish every second. I think the ping rate's every second to within 5 to 10 centimeters or more. It depends on what the grid looks like, but we can track them pretty accurately. And then my colleague Russ Perry is going to talk about survival within the entire delta. And of course, because these fish are very expensive and we're releasing 5,000 of them, we do both at the same time. So we get this very detailed information on where fish are going and how they're reacting to the velocity distributions, and then we also track them all the way to Chips Island and throughout the delta. Right. So as I described, we release fish over, I think this year we released them for 45 days continuously, and what this shows is that we basically release fish 24 hours. This is a clock here. The shaded areas are nighttime and daytime. And so way up at the city of Sacramento, we release fish continuously over the entire day and night. So the first thing you notice here is that when they arrive at the Delta Cross Channel, they are not arriving continuously. They're arriving mostly at night. They don't do much. They go off to the sides or do other things during the day, and they do a lot of their traveling at night. And I'll talk about that a little bit tomorrow as well. So here's what acoustic telemetry array looks like. I'm going to be talking about, that one doesn't move, about looking at spatial structures within an array that looks like this. Some of the best spatial structure data we have was when we were doing an experiment with DWR on a bubble barrier. It had lights and a bunch of other stuff. And so I just want to give you an idea of the kind of spatial structure that we have, and I'll talk about data from that experiment. This is bathymetry here. In Georgiana Slough. So this bubble barrier is here to try to keep salmon out of Georgiana Slough and continuing on the Sacramento River where the survival is higher. So if you just plot all the tracks, this is what you get. This is thousands of fish. Not a lot of spatial structure, is there? In fact, it's really hard if you're looking at individual tracks to kind of aggregate that in your mind. But what we can do is actually look at the number of fish that go through various cells under various covariate conditions. And this particular plot is a barrier off condition. We actually turn this thing on and off every day with the tide. The flows change a little bit every day, but not that much, and so we just turn it on and off every day with the tide at the same place in the tide, so we were able to pair it across various hydrologies and hydrodynamic conditions. Nevertheless, what I want you to see here is that most of the fish are on this side of the channel here. They are on the side opposite Georgiana Slough, and this is with the barrier off. This is the entire study, which, do you remember how long that was? Months.
It was 45 days.
45 days we're releasing fish, but fish were going through probably, 60 days maybe. And under a variety of conditions. All right. So this is, and one of the reasons why you do 5,000 fish is then you could spatially or temporally aggregate, right? But this is all of them, and you'll see in a minute why it kind of makes a good point. So that's what it looks like with the barrier off. You turn it on. So let me flip back and forth here. Boom, boom, boom. You can see the entire distribution is shifted away from the barrier when the barrier's on. So it moved from sort of in this, on the right side of the channel to way on the right side of the channel. And you can also see that there was some concentration at the end of the barrier and some other things. But my whole point is that what we want to do is take these very detailed spatial distributions under a variety of different covariate separations and then compare them to entrainment rates. And in this case, barrier efficiency. So then you could take the difference between those, and spatially, this is the difference between on and off over the entire study. And then, of course, again, we can divide it all up and slice and dice it. So big advantage of being able to collect, we were collecting hydrodynamic data at the same time and so forth. A big advantage about being able to collect everything at the same time and space scales. And that's the big challenge in doing biology, right, is that you usually can collect hydrodynamic information at really high frequency, and the fish data you can't. So here's the conclusion. What I want to say is two things. Fish don't go with the flow, partly because the arrival time distributions are not the same. They're just not coming through during the day, and they come through at night. So if you integrate over an entire day, you're not going to get the right answer. If you're integrating the flow over the entire day, you're not going to get the right answer. And then the second thing is that these guys are off to the side. I'm going to explain what this is in a minute. This is a streak. This is a critical streak line. Fish on this side of the on this side of the line, 88% of them we were able to predict 88% go in here. So under this condition, most of the fish are going to bypass Georgiana Slough anyway. So you've got to have, in order for fish to go with the flow, you've got to have basically a uniform spatial distribution. So there we go. So now I'm going to talk about, so that was fish distributions. Now I'm going to talk about trying to collapse the complexity of these very complex flow distributions that change over time. And this is something we call the critical streak line. And basically it's this line right here. You can see it pretty clearly. In this case, Georgiana Slough is actually the water is coming in from down below. This is very typical when the gates are open. It bypasses Georgiana, some of the flow bypasses Georgiana Slough and then goes into the Delta Cross Channel for a long period of time as a converging flow. And the challenge here for a fish is if it's doing this, you're going in. Unless you're way over here hanging out in the dock or getting eaten or something like that, you're going in. So this critical streak line was a way that we're trying to use to try and encapsulate a very, very complicated flow situation. So here's our little simple drawing. And again, I make the point that for fish to go with the flow, the distribution needs to look like this. And in Georgiana Slough, we find that it's not. It's biased to the far side. So the idea is that you figure out what this critical streak line is, and then you go to the bad side if you're on this side of the line, and you go to the green side if you're not. I should say at really high flows, Steve, the spatial, the turbulence scale is meters. We had trees that were cycling back and forth, and so right near this line, there's a fair degree of stochasticity, depending on when the fish enters the boil and so forth. But in any case, if you're way over on this far side, you're going into Georgiana, and if you're on this side, you're going down the Sacramento River, and you're going to have a better time. So this is a horrible slide, and I apologize for that. But what I want to do is I'm going to define three little ratios. One for conditions where the flow is coming from upstream and going into the cross channel, or going into any channel, and then bypassing it on the main channel. One flow ratio where everything is going in, and it does do this when everything goes in. It comes from the entire cross-section, both upstream and downstream, is going in when it's under these conditions. And then the other condition is when flow is coming from the other side. And what we wanted to do is we wanted to look at how long or how much water was going in to each of these channels under these conditions. And so these are basically flow ratios for these various conditions. And we wanted to, instead of using the flow ratio for the entire period, we wanted to disaggregate it into these three different conditions because it turns out the entrainment rate certainly is very different from here to any one of these. And to be complete, it turns out Georgiana only goes one way. And actually, it's even though I showed you those complicated patterns in the Georgiana and Delta Cross Channel junction, it's only weakly tidally affected. Almost every other junction in the Delta is more tidally affected than Georgiana and the Delta Cross Channel. So this can also happen, and does happen. Brad will probably show this. The water comes out. In fact, in some of the channels down the Central Delta, what goes in comes out is almost the same. And so we came up with a bunch of flow ratios for that too. So that's kind of the math behind it, and it turns out that these little pictures actually work pretty well. So what does this look like? So if you look at, this is Georgiana down here. This is the flow going into Georgiana Slough over time. And then if you look at each one of these ratios, you can see, and I've colored them, how much of the time and during what period these different things happen. So for example, the converging flow period for this is really long into Georgiana, and there are times where it's really short and then it bypasses Georgiana and goes into Delta Cross Channel. Super complicated, and what the heck is this going to do for us? What it does for you is then you can, and then I can show you that as the flow, this is a case where the flow is increasing. Pretty soon it's all coming from upstream, but during this time where it's reversing, you have these cyclings of converging or bypassing or whatever into Georgiana Slough. So this is a way for us to disaggregate it. So this is really, really messy. And in fact, if I look at the entire record of these ratios, I go, how useful is this going to be? Well, it's pretty darn useful after you actually go and take a tidal average of that. So you look at the amount of time over a tidal day that the flows are either coming in from upstream, coming from downstream, or converging. And what you find in Georgiana when the flows are relatively low is that a lot of the water, this red line here, goes into Georgiana during converging flow conditions. Most of it comes from upstream, as you'd expect. And then at high flows, of course, it's all coming in from upstream because there's no reversing flow. And so this is what I want to call your attention to. So we got into low flows, and then we opened the gates. So all of this period here is with the gates closed. And so when you open the gates here, it turns out that a lot of converging flow is happening in Georgiana, but when you open the gates, it changes dramatically. And so this is the point that I want to make, and that is that when you change the gates, okay, so this is what happens most of the time when the gates are open, and that is that the flow bypasses Georgiana and goes into the Delta Cross Channel under pretty strongly converging conditions. That's what happens when the gates are open. When the gates are closed, what happens is it moves that converging flow condition down to the Georgiana Slough. So the end of the story is very little net flow increase occurs in Georgiana Slough, but because the tidal velocity distributions change, the entrainment rate in Georgiana Slough goes way up. Because this happens a lot more when the gates are closed than when it isn't. And the net flow can't account for that increase in entrainment. This is kind of a complicated thing, but what I will say is the net flow is relevant to entrainment because it changes the tidal timescale velocity distributions in junctions. So it's not a direct effect of the net flow. It's the fact that you've actually changed the amount of time that water is going into Georgiana Slough under a converging flow condition. How am I doing on time? I've got one more. I could put it all together here if I've got like 3 or 4 more slides. Okay. I won't put it all together.
And I'm always on time. So.
You are? Okay. Okay. Why don't I go ahead and stop there? But maybe we can do this afternoon. What I was going to show you is that if we know the fish position in the entrance position coming into Georgiana Slough, and we know where this critical streak line is, we can predict whether the fish is going to go in Georgiana or not. The trick is that we need to understand what the temporal variation in spatial structure is as it enters the junction. In fact, I think I even have that on a concluding slide. I'm going to go through all these slides. Here it is right here.
John.
How's it going, Steve? I told you I'd cover some different stuff.
Waking up, thanks to the coffee. So that's pretty convincing. I guess one question that I would have come to mind, kind of a leading question, what does this mean then about when we do models to predict entrainment, tracking particles, when the models, say, assume complete mixing at the junction as opposed to the more details of the streamlines?
Yeah, it means you're probably not going to do too well. And if I'd shown those couple of slides where we disaggregated it, you can see that the velocity distribution is not completely uniform across the cross-section. You could see it in the spatial structure map as well. It's quite clear. And again, if those are the tools you have, that's what you need to do. So what we hope to do by doing these really detailed studies is come up with ways of characterizing the non-uniform spatial distribution, and certainly if there's day-night variability, we could characterize that and then apply that in some of these more simplified models.
So remember, I'm a fisheries person. So
And I'm a hydrodynamics person.
So can you control these streak lines by? Can you manipulate them?
You can change them significantly by the amount of net flow you have down and by the geometry of the channel. Those are the two ways of doing it.
Because people finally have me convinced that it's not net flow, that it's tidal, and now you're telling me it is net flow.
No, I'm telling you that the net flow controls the tidal distributions. I've got a really great slide.
He's going to have to explain it.
What controls net flow, though? That's the question.
Yeah. It's not directly the net flow. It's the net flow's effect on the tidal dynamics that's the important thing.
Again, the scales. Is it something that management can use? Is it within the operational dimensions of the system to manipulate those at certain junctions?
It could be, but water may not be the thing to do it with. We're doing a very simple barrier experiment where all we're trying to do is move fish across that streak line. We don't have to move them all the way across the channel, right? All we have to do is give them a little nudge across the streak line. If we find out that the spatial distribution is really, there's a lot of fish in that little narrow area, you don't have to move them very far and you'd be able to really reduce entrainment. So I don't know that you could do it with water, but I think you could do it with simple barriers. In fact, we're doing a simple boom barrier right now to try that. The other thing you could do is just permanently change geometry. Yeah. Finally, I'm going to give a talk on the effect of restoration other places tomorrow. That's one of the ways you might be able to do it. Actually restore something somewhere else and then change what happens at Georgiana and other places.
Thanks.
You bet.
Are you familiar with similar work on the Columbia River?
He is.
Apologize for being a microphone bad boy. The Columbia River community has been working on this problem for ages, and initially they started out with a premise very similar to this. And over time they noticed that there was other variables that were involved in governing the distribution of fish. And that's evolved to the point where they have structures now that literally can strip out fish from the water column. They're very effective. So they can capture maybe 60% of the out-migrating juvenile salmon with 10% of the flow. So it seems like you might be interested in enriching your approach with some of those findings.
Well, it's interesting. This boom that we're testing right now came from the Columbia River environment, and my colleague Russ Perry here works in that community. And when we first started doing these acoustic telemetry studies, we went and asked them to come help us, basically, because for exactly the same things you talk about. They understood the technology, we didn't, and then they also had a lot of experience. So the boom we're trying right now is actually one we borrowed from the Columbia River.
Okay.